everyone. So today we are going to talk about Module 2 of Chapter 4. So this one is going to focus on the visual system. So we'll be talking about the structure of the eye, we'll be talking about light waves, and how those light waves enter the eye, and then the physical characteristics of the light wave are kind of converted into the different aspects of vision. So we'll get started. So Module 4.2 is the visual system. So vision is known as the most frequently studied sense, and as we know, the eye takes in more information about the outside world than any other sense organ. The stimulus for vision is, of course, light, which either comes from the sun or light bulbs, but is also reflected off of other objects. There are three physical characteristics of these light waves that affect the three psychological dimensions of our visual worlds. So we'll talk a little bit about each of them. We have U, which essentially refers to kind of the color name when we describe things in terms of the color that we're seeing. We have brightness, which refers to the intensity, and we have saturation, and that one is a little trickier, but it kind of refers to how rich the color is. So I'll talk a bit more about that in a minute. So for U, it's basically what we talk about when we give a color name. So hue is specified by color names. It's the dimension that's related to the wavelength of the light. So when we have shorter wavelengths, so kind of more frequent waves, those would tend to be seen as blues and violets, while longer waves appear as oranges and reds. And if I had you in a classroom right now, I would kind of be drawing these on the board as we're going, but hopefully you'll be able to kind of see what I'm talking about from the figures within our notes. So basically, if you have a shorter wavelength, that means that the peaks and troughs of the waves are closer together, so the distance from one peak to another of a wave is a lot shorter, and that also means that the wave is kind of occurring more frequently. So in that case, we would see those blues and violets, but the longer waves, which would be the ones where the peaks are further apart, so it's kind of like a slower, less frequent wave, those are more perceived as kind of the red, orange, yellow end of the spectrum. So the sun actually produces a white light, which is a mixture of all of the visible wavelengths. So basically what happens is, depending on how they bounce off the objects, and basically what happens to the light wave when it bounces off the object, that is kind of how we determine the color that we're seeing. And it actually, sometimes we see that drops of moisture can act as a prism. So if you've ever seen a rainbow when it rains, that's basically because the drops of moisture in the air acting as a prism, which separates white light into all of the colors of the visual spectrum. So you see that kind of rainbow effect. You also might have seen it maybe in childhood, maybe in one of your science classes. I know I definitely saw it probably in like elementary school. They would show you kind of a crystal prism and how it reflects the light waves, and you can see all the different colors of the rainbow. So then we have brightness. So brightness is the dimension related to the amount or intensity of the light an object emits or reflects. So this intensity corresponds to the amplitude, which is the maximum height, of the light wave. The more light an object reflects, the brighter it appears. But brightness is also affected by the wavelength as well. So we do see that yellows tend to be brighter than reds and blues, even when the physical intensities are technically equal. So some colors will look brighter just based on the hue as well. So yeah, basically when we're talking about how bright something is, we're looking at the maximum height, so the height of a wave from its peak, which is the highest point, to the trough, which is the lowest point. And so that's what kind of gives us that measure of intensity or brightness. And then finally, saturation or colorfulness is the dimension related to the complexity of the light. So the wideness and narrowness of the range of wavelengths. So obviously, we typically, when we look at something, we don't just have one certain type of wave, light wave reflected at us. Usually there's a mixture of a bunch of different kind of wavelengths and wave amplitudes and things like that. So depending on how many different kind of types of wavelengths are hitting us at once, that would indicate kind of a higher complexity of the waves. So if we had light that contained only one wavelength, so it was reflected back kind of identically by every aspect of a particular object, it would be said to be pure. So the color would be completely saturated. The other extreme is white light, which has no color, and therefore we would consider it completely unsaturated. However, this type of pure light, or kind of fully saturated, is extremely rare in nature. So it's very rare that the light will be reflected in such a way that all of the wavelengths that are reflected kind of have the same length and the same amplitude. So usually we have some amount of kind of not saturation. We never really have the fully saturated. And you can kind of see this if you look at a television as well. You're able to kind of turn your saturation up and down. And so if you have access to a television with that feature, just try it out and you can kind of see what we mean by kind of completely saturated versus kind of completely unsaturated. The electromagnetic spectrum basically just shows us all the different wavelengths of lights that are possible. And you can see that the visual spectrum for human beings is very narrow. So it actually only goes from about maybe like 800, 850 to about 400 nanometers. And so that, if we look at it here, we also have kind of the infrared and the ultraviolet on either side. And you can see that that visible spectrum, if you look at the electromagnetic spectrum in general with all the different types of wavelengths, it is a very, very small portion of the electromagnetic spectrum. So the light that we can actually perceive as humans is very small compared to all the different wavelengths that are actually available. And then we see here in figure 4.8, you've got your light waves in the electromagnetic spectrum, so you can see what we're talking about by the wavelength. So again, you see that it's measured from peak to peak, and the amplitude is measured from the lowest point to the highest point of the wave. And so basically your wavelength would then be related to your hue or your color name, and your amplitude will be related to your brightness or your intensity. And again, figure 4.9 kind of really neatly puts all of them together, so you can kind of see what we're talking about saturation here. So the colorfulness, if it's fully saturated, it is that like the most kind of extreme pure version of that color, but as you have less saturation, it starts to be almost colorless. It gets kind of completely lacking in its color, right, like in the middle of the cone there. So with respect to the structure of the eye, and you don't have to remember every single one of these words, I usually do get students to label a diagram of the ear, which we'll talk about in the next section, but of course I'm not really doing labeling questions at this point. So really, it's more important for you to kind of just generally understand the names of these parts of the eye. So the sclera is the white outer surface of the eye, so you basically should be able to name them and give a brief description. So that's basically kind of everything that surrounds the colored part of your eye. Light enters the eye through what we call the cornea, which is the clear layer that covers the front portion of the eye and contributes to the eye's ability to focus. So you may have heard of people having a scratch on their cornea, so if something hits the eye, the cornea is that kind of clear layer that it's actually going to come into contact with. So it covers the front portion of the eye and contributes to the eye's ability to focus. And so when the light enters through the cornea, it passes through an opening called the pupil, which we all know is kind of the black portion of your eye. And that pupil regulates the amount of light that enters by changing its size. So you've probably all noticed that your pupils will dilate or constrict depending on what situation you're in, whether it's a low level of light or a high level of light. And so basically that happens because your pupil is kind of what decides how much light to let in at any given time. So if there's a lot of light, say if you're in a very bright room, your pupil tends to constrict, so it only lets in a little bit of light, because really in that type of scenario you only need a small amount of light. Whereas if you're in a very dark or dimly lit room, your pupils are probably going to dilate to let in as much light as possible, because there isn't that much light for them to let in at that point. So the pupil is kind of like the opening, and it can kind of expand or constrict depending on how much light it wants to let in at any particular time. And the size of the pupil is actually adjusted by the iris. So the colored part of your eye, whether it's blue or green or brown or whatever color, that part of your eye is the iris. And a lot of people think of it kind of as, oh, you know, well, it's just the colored section, but it is actually the muscle that causes the pupil to constrict or dilate. So it is very important in terms of the function of your eye. Then we have the retina. So the retina is basically right at the back of your eye. So once the light enters through the pupil, it then hits the lens, which is just behind the pupil of your eye, and it focuses the light onto the back of the eye. At the back of the eye is a surface called the retina. So basically the entire back surface, the kind of curve at the back of your eye, is labeled the retina, and it lines that inner surface and consists of specialized receptors that absorb light and send signals to the properties related to the properties of light to the brain. So basically what happens is the receptors, so the rods and cones in your retina, which I'll talk about in a minute, they are the ones that actually take in that light information and convert it from a physical light wave into a neural impulse, which is then sent back into the brain for processing. So as mentioned, the retina houses these photoreceptors for light. So there are two different types of receptors, and you should definitely know what they are and kind of know the difference between them. So we have our cones, which are our cone-shaped photoreceptors, kind of obvious, implied in the name, that are sensitive to different wavelengths of light. So I usually ask this question in class, but I'll kind of pose it to you and answer it very quickly myself. If they are basically sensitive to wavelengths, what do you think the cones are good at? They'd be good at the color aspect of vision, right? Because the color, or the hue, is related to the different wavelengths of the light. So the cones are the ones that are responsible for your color vision. And you kind of remember that if you think of like cone starts with C, color starts with C. So those are the ones responsible for color vision. There are about 7 or 8 million cones within your retina. Then we have our rods, which are, as the name implies, long and narrow photoreceptors. So they occupy the peripheral regions of the retina, and they're highly sensitive under low light levels. There are actually about 120 to 125 million rods in the retina, so there are quite a few more rods than there are cones. So cones are very sensitive to different colors. They enable us to have color vision, and kind of they're very kind of precise in that way, whereas the rods are the ones that would help us out in kind of a low light situation. So they're the ones that enable us to kind of have a little bit of a sense of night vision. So both of them kind of have their specialties. And then we have the fovea, which I'll show you in a diagram in a minute, which is the center of the retina, and it is where vision is the sharpest. So basically, if you look at the retina, if you kind of consider it as like a circle, as you go in towards the middle of the circle, you start to see a lower concentration of rods and a higher concentration of cones. So at the middle, or the fovea of the retina, you're going to have almost entirely cones, whereas as you reach the outer edges of the retina, it's going to be almost entirely rods. And you can see that in figure 4.1, oh my goodness, sorry, 4.13 here. So you see that if you're looking at the red is the cones, or sorry, I guess the red, green, and blue as the cones, and then these yellow ones are the rods. You can see that as you get further out towards the edges, it's entirely rods, and as you get closer to the middle of the retina, it's entirely cones. And then there's another diagram here from the textbook that just again kind of shows you those main components of the eye that we just talked about a little bit. So you should know what the lens does, what the cornea does, what the iris does, what the pupil does, and then kind of like the retina and the different types of cones that it contains. And I guess the fovea is that sharpest point that's in kind of the middle of the retina. So cones, as I mentioned, are able to distinguish between differing wavelengths of light. So, as I said, they allow us to see color, but they need a lot more light in order to function. So even though they're really good at distinguishing between different colors, they don't operate well in low light settings. So dark adaptation refers to the process by which our photoreceptors become as sensitive as possible in a dim light setting. So essentially it involves chemical changes in the rods and cones. So when you open your eyes, for example, maybe you're lying in bed at night and you're sleeping and you wake up, when you open your eyes, the first thing that your eyes has to do is kind of adjust to the low light in the room. And so basically what happens is that you're going to have changes within those rods and cones. And we do see typically that the rods tend to take a little bit longer to adjust to the low light. So the cones are typically the ones that kind of adjust first, and they enable you to kind of see, not very well, but at least have some sense of kind of night vision. And then after a few more minutes, your rods start to adapt as well. And at that point, basically your vision has gotten about as good as it's going to get in terms of your kind of dark vision, or your vision, your night vision, I guess. So the rods and cones are connected to cells called bipolar neurons, which in turn communicate with ganglion cells, and the axons of these ganglion cells make up the optic nerve. And I'll show you a diagram of this in a minute because it's kind of hard to conceptualize. So basically the optic nerve is a cluster of neurons that gather sensory info, they exit the back of the eye, and they connect to the brain. So information is carried through this optic disc, which is the area at the back of the eye with no rods and cones. So obviously there has to be like an area that kind of allows the light to exit the eye, and so there can't really be any receptors in the way blocking that kind of exit. So basically the optic nerve kind of goes back through that optic disc, and because there were no rods and cones in that optic disc, it produces a blind spot in the field of vision. There are no visual receptors in that spot. There can't be because the optic nerve has to exit there, and so therefore we do have a blind spot in our vision. However, we don't really notice them very often because obviously in most situations we have the use of both of our eyes, and the blind spots won't really overlap from one eye to another because of something called retinal disparity, which again we'll talk about a little later on. So here you can kind of see the structures I was just talking about within the retina. So it's kind of interesting because when the light hits the retina, it doesn't kind of hit the outer layer and kind of continue inward. It actually goes directly back to these cells right at the back, the ones that are closest to the kind of outer edge of the eye. So you see the rods and cones that are kind of represented in red there. And so the light will go back there and then move slightly forward to the ganglion cells, or sorry, the bipolar neurons, and then slightly forward more to the ganglion cells, and then kind of switch back around and start to go kind of loop back around back into the brain. So you can see those ganglion cells, which are represented by the orangish cells that are kind of closest to the center of the eye. You can see that those neurons of those, or sorry, the axons of those cells kind of loop back around and form that optic nerve, which then transmits a signal back to the brain for processing. So moving on, now we're going to talk a little bit about how we see color, so how our color vision operates. So there are actually two different theories of how our color vision operates, each of which occur at a different stage in the color vision process. So we have the trichromatic theory, which would occur during the first stage of the process, and then the opponent process theory, which would occur a little later on. So the trichromatic theory, which is also known as the Young-Helmholtz theory, maintains that color vision is determined by three different cone types that are sensitive to short, i.e. blue wavelengths, medium, i.e. green wavelengths, and long, i.e. red wavelengths of light. So it applies to the first level of visual processing, which is occurring within our retina, so within those cones, and we see thousands of colors based on the combined activities of the cones. So basically what they're saying is depending on which cones are firing and in what combination, that's what allows us to see the vast array of colors that we can actually perceive. So we see that something like total color blindness, which you've probably heard the term color blindness before. In order for color blindness to be kind of absolute, that would mean that the cones of the retina are either absent or non-functional, so it's typically some kind of genetic condition, and that is extremely rare. So typically when we're talking about color blindness, we're talking about people who are actually just color deficient. So they're unable to distinguish things like red versus green or blue versus yellow. And we do see that color deficiencies are more common in men simply due to the way that they're inherited genetically. So this kind of illustrates the trichromatic theory a little bit there for you. So again, we'll have those three different types of cones. The one that's more sensitive to the long wavelengths, so things that are kind of like more on the red end of the color spectrum. The one that's kind of more sensitive to medium wavelengths, so kind of around the green area of the color spectrum. And then the ones that are more sensitive to short wavelengths, which would be more the blue and purple end of the spectrum. The opponent process theory, on the other hand, applies to the second stage of color processing. So the trichromatic theory is actually occurring within those three types of cones. So that's occurring within the retina itself. So then once the light wave information is kind of translated into a neural impulse and starts to be sent back towards the brain for processing, as I mentioned earlier, it goes from the cones to the bipolar neurons and then to the ganglion cells. And the the axons of the ganglion cells are what kind of come together to produce that optic nerve. So basically, the opponent process theory would be occurring within the ganglion cells and the neurons within the brain. So a little bit later on in the process. So at this point, the physical light waves have already been kind of transduced using that transduction into neural impulses. And so this theory would state that we perceive colors in terms of opposite ends of the spectrum. So red to green, yellow to blue, and white to black. So basically, this theory would state that the cells, which are known as opponent process cells, either respond to short waves and are inhibited by long waves or vice versa. And based on the combination, again, of those cells and which ones are firing and which ones are inhibited at any given time, again, they combine to give us all the colors that are visible within that spectrum. So basically, the color code that results from all these firings or inhibitions is then passed on to higher visual areas for processing. And the opponent process cells that are inhibited from firing in the presence of one particular color will create a burst of firing when that color is removed. And those that fire stop when the color is removed. So basically, the ones that were prevented from firing, as soon as that stimulus is kind of removed, they're going to automatically have kind of like a rebound effect. And basically what this does is it creates a negative afterimage. So if you look at this picture here, this is kind of an example of a negative afterimage. You've probably seen one before at some point. But if you stare directly at this white dot and avoid looking away, and then after about a minute, all of a sudden you shift your focus to something that has a white background, you should actually see the opposing colors from this flag. So I'm going to actually let you do this. I'm going to pause here, and I'm just going to let the video run for like a minute, and you can stare at this picture, and then I'm going to flip to the next slide, which is a white background. So try your best to focus on that white dot and not to blink if possible. And I'll give you, 30, 45 seconds, and I'm going to switch to the next slide. So you can start now. So we're coming up on about 45 seconds, so keep staring at that white dot, and I am going to change the slide right now. So hopefully what you're seeing now is basically that negative afterimage. So what you'll be seeing is the opposites of the colors you were looking at. So if you were looking at blue in that picture, it should be showing up as kind of a yellowish. If you're looking at green in the picture, it should be showing up as kind of a reddish color. And any areas that were black should be white or vice versa. And so essentially what it does in that case is that you should actually be seeing the American flag as it typically looks, rather than that inverted color that we just saw. So basically that's just an example of that rebound effect from those opponent process cells. So because if you're staring at green on that picture, for example, and you're staring and staring and staring at it, the ones that are sensitive to green are firing, but any that are sensitive to red are inhibited, so they're stopped from firing. So as soon as you remove that green stimulus, automatically the red ones start to fire, and that's basically what creates that negative afterimage. So some common vision disorders, and I'm not going to get into this basically to show you this diagram, but obviously you've probably all heard of nearsightedness and farsightedness, and essentially I just wanted to kind of let you know that basically what causes them is actually a misshapen eye. So if your eye is elongated or your eye is too short, then the images are not centered properly on the retina, and that's what can cause issues in terms of like nearsightedness and farsightedness. But again, that's not really something I'm going to test on. It's just something that might be of interest to you. It definitely is to me because I do have issues with my vision. Obviously, I wear glasses and contacts, so I find it kind of fascinating. So in terms of constructing our visual world, we're not actually seeing the retinal image. So you might have noticed when I showed you a picture of the retina earlier in that image, it actually flips the image upside down. So what happens basically is, for example, if you were looking at maybe a water bottle that you had held right side up in your hand, the image that's actually presented on your retina, when it goes through the lens, it flips. So in that respect, the image on your retina would actually be a water bottle that is upside down. But then when it goes on to processing in the brain kind of automatically corrects for that difference. And so you perceive it as being right side up. So basically, the brain is taking the sensory signals from all of our sense organs and transforming them into a unified model of the world, which is essentially what we call perception. So we use principles from form perception, depth and distance perception, and visual constancies to help us make sense of the visual input we take in. At times, unfortunately, perceptual constancies can be used to trick us into thinking that we see something we do not, or into interpreting an image incorrectly, thus creating an optical illusion. So like that Necker cube that I showed you at the beginning of the last module, that would be kind of an example of an optical illusion. I'm sure you've seen a lot of them over the years as well. I used to love looking at those books when I was a kid. So now we're going to talk briefly about something called visual constancies. So perceptual constancies in general refer to the ability for us to perceive objects as having a constant shape, size, and color despite changes in our perspective. So basically what this is referring to is that just because, for example, the image on our retina changes because something is kind of in motion or kind of engaging in kind of a different perspective of it, that doesn't mean that the properties of the object itself changes. So it kind of makes sense because if you think of something that's constant, that's something that kind of remains the same. So in terms of shape constancy for vision, that's basically talking about the fact that items still maintain their shape despite your point of view. So for example, if you were looking at a door of, say, a bedroom or an office, and you were looking straight on and the door was closed, you probably perceive that door as kind of a perfect rectangle, right? You're looking at it and you see that it has a rectangular shape. However, if that door is slightly ajar and the door is kind of angled towards you, when you're looking at it, you're not actually seeing a rectangle. You're seeing something that is kind of more like a weird quadrilateral because of the angle of the door. However, we are aware that the shape of the door didn't change just because our perspective on it changed. So the fact that we're able to say, okay, even though it doesn't look like a rectangle now, it's having a different kind of image on my retina, it still is rectangular, that would be an example of shape constancy. Another example of visual constancy is location constancy. So stationary objects remain in the same place as we move. So when we're kind of flying down the highway and there are trees or there are fields or whatever on the side of the road, when we zoom past them, it looks like all that stuff is kind of moving backwards, right? But we know that the trees and the roads and the farms, they're not actually moving. Even though we perceive them as in motion because we're in motion, we know that the location of those objects still remains the same. So that would be an example of location constancy. The third is size constancy. And so this one is kind of best conceptualized if you think of, say, a friend walking towards you. So maybe they're 100 meters away or 100 feet away when you notice them. And at that point, they probably look pretty small to you. In the same way that, if you were flying in a plane and you look down, the cars and buildings below you look like kind of little ants or very small things. So the closer we get to something, the larger it appears to us. However, if you have that friend who's walking towards you, and at first when you see them, maybe they look like they're only kind of like take up a centimeter of your vision, and as they walk closer and closer to you, they appear to get bigger. But we know that they're not actually increasing in size, that it's basically the fact that, again, the image of them on our retina is changing in size, and that's what's kind of leading us to perceive them as increasing in size. So we're able to know that the size is actually remaining constant despite the fact that the retinal image is changing. The fourth is brightness constancy. So for example, if I was in a dimly lit room and I had a red apple in my hand, because of the dim light source and the fact that there aren't that many light waves bouncing off it in that room, that apple is probably going to look like a pretty dull red, even if it was kind of a very vibrant red under normal light conditions. However, if I bring it outdoors and it's a very sunny day, then that apple is probably going to look a lot brighter. It's going to look a lot more intense in color. But we know that the actual brightness of the color didn't change. It's simply due to kind of the setting in which we viewed it. And then finally, color constancy, which is very related to the brightness constancy. We know that the actual color itself didn't change. So not only did the brightness of the color not change based on the lighting level, we know that the color itself also didn't change based on the lighting level. We might say, wow, you know, that color is a much brighter red or brighter yellow than I imagined, but we don't think that the object magically changed color just because we're viewing it under a different light source. So here are some of the examples of those constancies that we just discussed. So the first one there, you can see that shape constancy. So we're perceiving that door to be a rectangle despite the fact that the actual outline of the image on our retina changes. The second kind of illustrates color constancy. So even though the colors on the far side of the balloon look kind of a lot duller and maybe kind of less bright in terms of their coloring, we know that it's just because the light source is not hitting them directly. And then the third one here shows that size constancy. So you can see that based on if we were to take that person in the size that he appears at the top of the photograph and then bring him down to the bottom, it would appear that he's very small compared to the children in the photograph. However, we know that his size is actually a normal size. We can tell by looking at that picture that the only reason he looks smaller is that he's further away from us. So the fact that we're able to keep all of those things constant in our mind, despite those changing kind of actual images on our retina, is a testament to kind of the efficiency and effectiveness of our sensory systems. So finally, for this section, we're going to talk briefly about depth and distance perception. So usually when we're looking at something, we need to know not only what it is, but also where it is. So if it's close to us, if it's far away, you know, where it sits within the plane. And we're able to infer an object's location by estimating the distance or the depth to it. So binocular cues rely on the use of both eyes. So you can think of binoculars, if you've ever used binoculars, they are something that you look through with both eyes. And so basically, these cues give us an estimate of distance or depth, so how close or far something is from us, by using cues that rely on the use of both of your eyes. So one is called convergence. And again, this is something that I kind of usually demonstrate in class when I'm talking about this stuff. But you can kind of do it yourself. You can imagine what I'm doing. If you put your finger about a foot from your face and you start to pull it in closer and closer to your nose, you can kind of feel your eyes start to converge. They start to kind of turn inward towards the object, right? So in that way, our brain is able to tell based on the amount of convergence whether our eyes are kind of narrowing in or they're kind of expanding outward. That'll basically tell us how close or how far something is from us. So the closer that an object gets to us, the more those eyes will kind of tilt inward and converge onto that object. And then we have retinal disparity. So retinal disparity is the difference in relative position of an object as seen by both eyes. And again, that provides information about the depth and the distance that that object is from us. So again, something I typically show you, but if you hold your finger up in front of your face and you kind of blink one eye and then the other back and forth, you can see that your finger almost seems to jump back and forth, right? It seems to change location. And again, depending on how close or far away the object is from you, you end up having more retinal disparity, so the object looks like it really kind of jumps back and forth a lot, or you have less, so it doesn't seem to move much. And again, that's something that your brain can use to kind of estimate how close or how far something is from you. Then we have monocular cues, and so if binocular cues are distance cues that rely on the use of both eyes, mono usually means one, so monocular cues are depth cues that we can perceive with only one eye. So we don't actually need that sense of kind of depth perception that's given to us by both of our eyes. Of course, you know, if you only had the use of one eye, you would lose the binocular cues, but you'd still be able to use monocular cues in order to be able to estimate distance and depth. So one of the first ones is kind of the easiest to explain, interposition. So basically an object that is in front of another object blocks the view. So if I hold up, you know, my water bottle in my left hand and then right behind it I hold up a pencil in my right hand, I'm probably either not going to be able to see that pencil or I'm only going to be able to see a little bit of the pencil. It's going to be blocked by the water bottle. And in that way, I can tell, okay, well, the water bottle actually has to be closer to me than the pencil. Otherwise, it will be the other way around and the pencil will be blocking the water bottle. Linear perspective is another one that's very commonly illustrated. So you've probably seen a picture of train tracks or a road, and how even though we know the sides of that road or the sides of the railway track are parallel, they seem to kind of slightly converge in the distance. So it's almost like they start to point towards each other. And that is another way that we can estimate distance. So the closer something is to that point where those two lines intersect, that we know are parallel, the further away that that item is from you. And finally, we have height in plane. So typically, and we kind of saw this in the example with the man a few minutes ago who was on that bridge, the things that are higher up in the picture tend to be further away from you. So in that case, it was a bridge and the kids were closer to us. And the fact that he was kind of higher up and also that he was smaller, like we pointed out with the size constancy, would be some cues that we could use to understand that he is much further away from us than those children were. And finally, we'll talk very briefly about visual illusions because they're based on a lot of the things that we just talked about. So when our knowledge of perceptual constancies causes us to be fooled or tricked, we call it a perceptual illusion. So obviously, because our brain knows these things and kind of perceives them as fact, when some kind of picture or image messes with them, then that's what we would call a visual illusion. So perceptual illusions occur when the strategies that usually lead us to accurate perception are overextended to situations where they no longer apply. So for example, if you look at this quarter illusion here, well, I just finished telling you that something that is closer to that kind of convergence of those two parallel lines, which the top apple is, and something that is higher within the plane, which again the top apple is because it's higher up in the picture, that it typically tends to be perceived as smaller because it's further away. So typically it looks a lot smaller than the one that's closer to us. So what this does to us is our brain uses that information to say, well, because it's high up in the image and because it's closer to where those parallel lines are going to kind of intersect, then that would tell us that it's further away. And so what your brain does then is that it compensates for it being further away by thinking that, okay, well, you know, it must actually be larger than it appears in the picture. So a lot of people would look at this picture, and if you ask them if the apples were the same size, they would say that the top apple is much bigger than the bottom apple. Whereas if we took both of them and put them on top of each other, they'd be the exact same size. But it's because your brain automatically assumes that the apple must be further away because of those cues, and therefore that it should be looking smaller because it is further away, then that's what kind of tricks your brain into thinking that that apple in the back must be much larger than the one that's closer to you. Sorry, I probably did kind of a weird job explaining that, but hopefully you can kind of see what I'm talking about there. So that is it for Module 2, and the next two modules are pretty short. The third module will go through a bit of stuff on hearing. There isn't quite as much as the information on vision, because as we mentioned, vision is the most studied sense. And then we'll talk very briefly about the vestibular system. And then in the fourth and final module, again, we'll talk very briefly about your sense of taste, sense of smell, and a little bit about the sense of touch. So those won't be nearly as long as these first two, and hopefully you're kind of enjoying this chapter so far. I know that a lot of it can get a little bit confusing at times, but definitely if you have any questions, feel free to reach out either during class when I'm having those little chat rooms, or if you want to kind of book a little Zoom meeting with me to go over any of this stuff, by all means let me know and we can kind of arrange something. Other than that, I will be having yet another kind of review class at the end, and then I'll probably have another final little review class before your actual final exam, maybe like the day before or something. So hopefully we'll have plenty of time to go over this stuff before the exam. Other than that, I hope you've enjoyed this chapter so far, and I will talk to you in the next video.